I'm going to talk about linear imaging theory in the context of elastically scattered electrons and how we can interpret images that come out of an electron microscope, both a transmission electron microscope as well as a scanning transmission electron microscope. The recommended reading for this would be the first couple chapters of Advanced Computing and Electron Microscopy by Earl Kirkland. And in this book, you'll be able to see some more details that I'm covering today, of what I'm covering today. And I want to start not in real space where we see individual atoms and the distances between them, but rather in reciprocal space where diffraction patterns represent the long-range order and packing of crystals. And it was a diffraction pattern that validated that atoms, in fact, do exist as periodic arrangements. And this was first hypothesized scientifically by Kepler, that thought that the packing of atoms could give rise to facets and geometric shapes that are represented in snowflakes. But this wasn't validated until hundreds of years later, where von Laue and his collaborators showed that the diffraction pattern, in fact, has discrete peaks that represent the discrete nature of crystals. To understand how a diffraction pattern is formed, first consider a disturbance in three-dimensional space, a spherical wavelet, so this radially propagating wave that can be represented by an exponential term with a frequency, spatial frequency, a position r in space. The wavelet is located at the position r prime, and the overall intensity of this wave decays as 1 over r. So we have this radial oscillating wave function. And if we want to think about more complex wave functions like wave fronts, plane waves, or plane waves with curvature added to them, we can use the Huygens principle, which states that a superposition of wavelets can be used to construct one of these wave fronts. So if you want to construct a wave front, you can just place a bunch of these spherical wavelets to create constructive and destructive interference conditions where a wave front will exist with a constant phase. So the solid lines here represent wave fronts of constant phase. We can also use wave vectors to represent the local direction of that wave at a particular point. And to construct the wave vectors, they're just vectors pointing normal to this surface, this wavefront surface. Right? What happens to this wave when it's incident upon an aperture? We can call this wave at the aperture psi of r prime, and the aperture function a of r prime. And we want to know how this wave function then scatters through this aperture. We'll use r prime to denote the two-dimensional spatial coordinate on the aperture. And we're going to look at what the wave function looks like at a far distance away, psi of k. So on this distant plane, what is psi of k? Consider the contribution that each wavelet might make to a particular position at this distant plane and add up all those contributions. So it's a double integral across our aperture function of our wave front and all the wavelet terms. And so this is kind of a messy double integral, but we can make some simplifications if we consider this plane to be very far away. We can do some expansions, and in the far field what we see is these r prime terms, these two spatial coordinates that are making this integral a little messy, simplifies, and we get a single expression where psi of k, the scattered wave at a distant plane, is a double integral of our aperture function and our wavefront with this exponential I to the k dot r. Now this functional form for the far field diffraction is exactly a two-dimensional Fourier transform. And a two-dimensional Fourier transform is a known mathematical tool for taking information in real space and turning it into reciprocal space. So what do I mean by that? If I have a function in real space, say f of x, we have intensities that are mapped to positions in space. And the Fourier transform will map that information to intensities and phases in reciprocal space, in frequency space. And we can go back and forth using an inverse Fourier transform and a Fourier transform, taking us from real space to reciprocal space. So to see what this looks like, we need to get some intuition about what functions look like when we go from real to reciprocal space. So consider a one-dimensional slit where we have a value of 0 everywhere except for the square pulse where the value goes to 1, some non-zero value, and it's confined to a dimensional width of a. The Fourier transform of this function will be a sinc function, so sine over sine of as a function of A and Q, Q being the frequency, divided by A and Q, and it has a width associated that's 1 over A. So here we have a width of A, and our sinc function has a characteristic width 1 over A. And we can extend this to 2 dimensions, so we can add radial symmetry to this slit. In this case, I'm starting out in Fourier space, and I'm saying my slit has a maximum frequency K max. When I Fourier transform it, I get something that's very similar to a sinc function, but it contains a first-order Bessel function. Still similar behavior with a radial symmetry. And I want to make this point that we have characteristic dimensions in one space, say K max, gives us a characteristic dimension that's the inverse of that. So we'll call this reciprocal space or frequency space when we're talking about Fourier space, and we'll say real space when we're talking about positions in real space. So what we see is dimensions in real space are inversely related to dimensions in reciprocal space. And to illustrate this, I like to use the structure of DNA, which was a Nobel Prize winning work by Crick, Watson, and Wilkins. Photo 51 was the X-ray diffraction pattern of a DNA structure. And what they were able to do was correlate this principle of reciprocity to understand the double helix structure. So here we have these peaks that are occurring at low frequencies, so the peaks close to the origin correspond to the large distances in the chiral DNA structure, the repeat of the chirality of the structure, and then the peaks out at farther distances in the diffraction pattern correspond to small distances associated with the base pairs. So we see this principle of reciprocity where distances that are small in reciprocal space and frequency space are large in real space. And it's not just X-rays that diffract, it's electrons that diffract as well. And it was first demonstrated with Thomson as well as Davidson and Germer that electrons in fact do have an inherent vibration frequency that's proportional to the energy. This was proposed by de Broglie. And in the previous lecture, we heard that it was obvious, but it wasn't so obvious to people at the turn of the century. Right? This was the experimental foundation to quantum mechanics. It demonstrated that matter, in fact, behaves like waves. And Kikuchi, shortly thereafter, would use this tool to map to understand crystallographic structure where the spacing and the intensities of these peaks reflect the spacing, intensity, and symmetries of crystals. And we're still using this now routinely in electron microscopy to discover new states of matter, such as quasicrystals, which Dan Shechtman discovered in the 80s, earning him a Nobel Prize in physics as well. Right, so there's another way we can get a diffraction pattern, not just simply from the far field, but also through the use of a lens. So a lens will take positions in one plane and will map them to positions in the image plane. But rays that come from this object plane will be focused to a point on the optic axis if those rays go parallel. If rays come off at a particular angle, say alpha, those get mapped to a different position. So this plane where the angles are being mapped to a particular location is our back focal plane. So a lens can be used to map particular angles to positions. And what this effectively is bringing our diffraction pattern from infinity into the back focal plane. So the lens is mapping angles to positions. Those angles correspond to wave vectors in our wavefront. So it's effectively giving us a Fourier transform. Now these wave vectors they are vectors, as are the angles, and the overall spatial frequency will also depend on the wavelength. Okay, so a lens can give us a Fourier transform too. And this was the tool as introduced in the previous talk. This is what allowed the construction of the first electron microscope by using electromagnetic lenses. They could exploit the fact that the electrons have picometer wavelengths well beyond that of visible light and push beyond to atomic resolution. And so we saw that a stem can provide what historically was one of the first demonstrations of imaging individual atoms on a thin amorphous support. In this case, the heavy thorium atoms appear as bright spots, and some of those bright spots correspond to a single individual atom. This is an annular dark field stem image. Another image, as an example, is a TEM image here of a double-walled nanotube. the walls of the nanotube appear dark on a brighter background, and we can count the walls in the nanotube. So this opened up a field, whole new field in nanoscience, earning a Kavli Prize. Okay, so these are two principal instruments for high-resolution transmission electron microscopy: the TEM and the scanning transmission electron microscope. So we saw much more complicated ray diagrams than this of the TEM. This is a simplified version of what we saw. We have a source with a parallel or nearly parallel illumination upon the sample. It scatters through the sample into an objective lens and an aperture placed on the back focal plane. And this lens-aperture combination forms an image onto a detector. This could be a phosphor screen. This could also be a camera with pixels. If we run this instrument in reverse, we get the geometric optical diagram of a scanning transmission electron microscope. So in this case, we have a source coming from the bottom, going up through our aperture and objective lens. It's then focused onto the sample, scatters through the sample into a detector. Now, we might have many different complex detector geometries, either on the axis or, in the case of annular dark field TEM, off axis. If the detector's on axis, it's equivalent. You'll get an equivalent imaging mode to TEM. If it's off axis, as we'll learn in the case of an annular dark field detector, it can give you an incoherent image. So the TEM, this idea that electrons come from the top, go down to the bottom in TEM, and from the bottom and top in STEM, isn't necessarily true, but in these two instruments it is. So this TEM, the electrons here start at the top, propagate down the instrument, and neon instruments, which are dedicated STEMs, they only operate in STEM mode. The electrons start at the bottom and do, in fact, go to the top. But this idea of reciprocity, the fact that you can take the ray diagrams back and forth, is here to just build your intuition for the relationship between these two instruments. So how is an image formed? The way we think about image formation in an electron microscope is through a linear imaging model. So linear imaging model takes a function, say f of x. This is your object. It's your specimen. It might be at atomic length scales. It might be a nanoscale image. And then it goes through your electron microscope. And this acts as a blurring function. The optics in your microscope will alter this object function to create an image. And so how do we go from our object to our image, and what is this blurring function? We can describe this blurring as a convolution between our object and some function that describes our microscope, in this case h of x. We call that h of x the point spread function. So if we convolve our object with h of x, that mathematical operation is an overlap of our object function with this blurring function, and we then roll that blurring function across our object. And I'll explain that in the next slide. This integral is kind of complicated to think about if you're not familiar with convolutions. In reciprocal space, this operation is quite easy. So if we take the Fourier transform of this convolution, it's simply represented as a multiplication in Fourier space. So the Fourier transform of f of x is f of k. The Fourier transform of h of x is h of k, and we multiply them. The Fourier transform of this point spread function is called the contrast transfer function. So I'm going to use this jargon a lot in this talk. When I talk about point spread functions, think about blurring in real space. When I talk about contrast transfer functions, think about multiplication in reciprocal space.
And reciprocal space is the diffraction pattern in the back focal plane.
That's right. So when I talk about reciprocal space, I'm talking about this back focal plane. And when I'm talking about real space, think your specimen. We're most familiar with real space. We exist in real space. We think about the arrangement of people in this room relative to each other. Frequency space is more complicated. We have to then think how we can be represented as a sum of various frequencies. Okay, so convolution of two functions. So let's just pick two arbitrary functions that have finite size, f of t. If we want to take a convolution, what you'll do is you'll insert a dummy variable and you'll invert one of the functions. You'll then apply a shift to that function and multiply it with the other function and measure the area under the curve of this multiplied function. And you'll do that for all shifts. So this best illustrates a convolution. So I have two square pulses. As one square pulse is rolled across the other, it begins to overlap, so our convolution function goes up in intensity. It reaches a maximum where the two overlap the most, and then the value decreases back down. Now, these functions don't have to be the same or symmetric. Here's another example of two functions that aren't the same. So one function overlaps the other. We again see the intensity go up. So the black curve, again, is the convolution of the blue curve and the red curve. Okay? So this is a graphical illustration of a convolution of f and g, or of the blue function and the red function. Okay, in reciprocal space, what's happening? In frequency space, what's happening? That's described by the contrast transfer function, which is the Fourier transform of our point spread function. You might see the contrast transfer function normalized to the zero frequency level, but either way, what I want you to understand is the functional form of a contrast transfer function and how it impacts our image. So one functional form that's good to know about is a low-pass filter. And in a low-pass filter, we have a value that decays as we go to higher frequencies, as we go to higher wave vectors. You can think of this as a division in Fourier space, which will give you an integration, a smoothing effect. That is, we're emphasizing low frequencies and we're de-emphasizing high frequencies. In a high-pass filter, we're increasing with k. You could think of this, for example, as a multiplication by k in Fourier space, which maps to a differentiation in real space, but it's an edge-enhancing process. So we're emphasizing the high frequencies, we're de-emphasizing the low frequencies. So let's see this actually play out in an image. So it can be any image. It doesn't have to be a micrograph. We can take just a photograph of a nearby region. And you look at the Fourier transform of this photograph. You can do this on your computer today. And you'll see that most of the information lies at zero frequency. So the center here is low frequency, zero frequencies in the image. And as we go out to the corners and the edges, we're going to higher frequencies. If we apply a high-pass filter, we're going to suppress information at the lower frequencies, giving additional emphasis to the higher frequencies. So this is what that multiplication looks like of our Fourier transform and our filter. So we see that the low frequency information has been suppressed, and we can now see the contrast in the high frequencies. When I take the inverse Fourier transform of this masked Fourier transform, we get an image that is fairly gray. Most of the information is missing in the image. However, what does remain is contrast at the edges. So I don't know if you could see it, but you can see sort of white and dark lines that correspond to the high contrast edges in the original image. Right? And that's because these edges are sharp and they contain high frequency information. The other contrast transfer function we just talked about was the low-pass filter, and in this case, it's complementary to the high-pass filter in that it emphasizes the low-frequency information. So now we see that low-frequency information has been amplified, and when we take the inverse Fourier transform, we get something that looks a lot like the original image, except for it's blurry, it's fuzzy. So if you do any of these image filtering techniques on your images, these are the sharpening and blurring filters you might see. Maybe you have a slider on your Mac that allows you to adjust sharpness. It's applying these filters. Okay, so how does a point spread function and a contrast transfer function play out in an electron microscope? So let's consider a coherent imaging condition. This could be a TEM or a bright field stem image. Here I'm showing a diagram of a TEM where a plane wave is incident upon the sample. This plane wave has very little convergence, and when it passes through the specimen, we get this term psi object. Psi object is a wave function that represents the structure of our specimen. That wave function that represents the structure of our specimen, psi object, then passes through an objective lens and through an aperture on the back focal plane. When it does this, we go, as we learned, a lens will take us to Fourier space on the back focal plane. So we've now taken our object function and we've gone to reciprocal space. We've gone to Fourier space. And it's passed through both a lens, and an aperture. And that's represented in this multiplication of our object function, the Fourier transform, with our aperture. So just like in the diffraction we saw at the very beginning, we had an aperture, A of k, multiplied by our wave function. Same thing. Then when we go to the image plane, we undergo an additional Fourier transform of this whole term. So now when we have a multiplication in reciprocal space, we have a convolution in real space. So that object function that represents the structure of our specimen is now being convolved with our aperture function, which contains the shape of this aperture and a little bit of information about the lens as well. What we measure ultimately is that amplitude squared. This is just a fundamental property of quantum mechanics, that what we measure is the probability density of a matter wave, and that's described as the amplitude squared of our wave function. So this psi image squared is what we see on our detector, on our camera. Okay, so we're seeing how convolutions play out in the TEM. Just again, a reminder that this aperture function A of k is our contrast transfer function, and in real space, when we're dealing with convolutions, A of x is our point spread function. That was an imaging mode for coherent imaging, like in TEM. We can also have an incoherent imaging mode. To have coherent imaging mode, to have a coherent imaging condition, we need to consider the angular spread beta of our microscope, and it defines a coherent length. If our coherent length is large relative to our image resolution, we'll have coherence. So in TEM, the illumination angle is going to determine your coherence, and your collector angle and stem is going to determine your coherence. This again is the principle of reciprocity. We see a relationship between the illumination angle in TEM, the collector angle in stem, and term beta is measured relative to alpha. So we need to think about our coherence length in relation to the spacing in our specimen. So we can link these two equations and get a condition for coherent imaging where beta needs to be much smaller than alpha. If we get that, if we have a coherent imaging condition, then all the waves that scatter will interfere with each other. That is to say, we have to take the amplitude squared of all of our wave functions. Let's look at two wave functions, psi A plus psi B. The amplitude squared will have the intensity of psi A, the intensity of psi B, and cross terms. So these will get interference effects between waves. In incoherent imaging, when beta is much larger than alpha, turns out beta needs to be about 3 times alpha. So beta needs to be much larger, 3 times the size of this term alpha. And in this case, we can just deal with the intensities of each individual wave. So why is that useful? So yeah, just to summarize, we have coherence is controlled in TEM by your condenser aperture and your collector aperture, and resolution, as we'll find out later, is determined by this objective, the angular spread in your objective aperture. Okay, so incoherent imaging, the model is a little different. In this case, we have our object function. Its intensity squared is simply convolved with the intensity squared of our point spread function, of our aperture function. In reciprocal space, our contrast transfer function is the Fourier transform of A of x, which is just a self-convolution with its complex conjugate. So what we measure ultimately to get our image is the convolution of our object with our point spread function, which is our aperture function squared. So we convolve intensities, we measure intensities. Okay, so we can summarize this by the point spread function in coherent imaging is simply A of x. In incoherent imaging, it's the intensity squared. A contrast transfer function is the Fourier transform of that. So this function will have both real and imaginary components. However, the contrast transfer function in incoherent imaging will not. It's simply, it will simply be the convolution of A of k with its complex conjugate. And in this case, we need to convolve our point spread function with our object for coherent imaging, then square the amplitude. And with incoherent imaging, we simply convolve our object intensity and then our point spread function. Okay, so talked about coherent and incoherent imaging, introduced a linear imaging model. How does this play out in the context of resolution? So when you talk about resolution, some people jump immediately to pixelation, how many pixels you have. And that is a definition of resolution. It is something you must consider. The Nyquist limit describes what the maximum resolution you can have at a given sampling rate. So sampling in the case of an image, just think pixels. The maximum frequency you can obtain is inversely related to your pixel size with a factor of 1/2 in front. So that is, to simplify that, if you want to resolve two objects, you need more than just 2 pixels. You also need pixels in between those two objects. But the Nyquist limit is easily resolved just by increasing your sampling. So more pixels on your detector, more sampling, more beam positions in STEM, more pixels in TEM. But microscopists are usually talking about optical resolution when they're talking about the resolution of a microscope. That is, what is the limit which we can resolve 2 finite objects, say atoms, in this case silicon 110, and with a 1.35 angstrom spacing between atoms. As our source size gets larger, the clarity of these 2 atomic columns that are adjacent get more and more blurred, and eventually we won't see the atoms. So what determines resolution, our ability to see atoms in space? Let's think about it in the context of an incoherent linear image. So again, in the incoherent linear image, we have our object convolved with our point spread function. Our object might be atomic columns, like the example I just showed. Our atomic columns are these sharp peaks that represent the nucleus of each atomic column. And our point spread function, in the case of STEM, would just be our probe shape. So in STEM, we're scanning this probe across atomic columns. When our beam hits an atomic column, the convolution will provide the shape of our point spread function, which is this airy disk-like function. And if we have 2 columns next to each other, we'll have 2 of these airy disk peaks that overlap and give a central minimum. That's non-zero. So in the well-resolved case, let's consider 2 atoms far apart, say a couple angstroms. As we bring them closer and closer in an incoherent linear imaging model, we simply add each peak. When they overlap, that central minimum will start to rise. It will rise to a point that is defined as the Rayleigh criterion, and that's a critical point where if the atoms get any closer, or the resolution, rather I should say, if the resolution gets any worse, then the peaks will move inward, and the position of these peaks will no longer represent the actual positions of the atom. So the Rayleigh criterion is a good criterion for defining resolution. In practice, we just say if you have 26% contrast in this central dip relative to the 2 peaks, it's resolved. You could continue bringing those atoms closer, and eventually that central minimum will flatten out. That's the Sparrow criterion. If you continue bringing them closer, you'll just have one single peak. So it's certainly unresolved at the Sparrow criterion, but the Rayleigh criterion is the best practical use for defining resolution. All right, so what defines the shape of those airy disk patterns I just showed? That's set by the convergence angle of your lens, the size of your aperture. We saw that the Fourier transform of a circle disk gives us a shape like this. Right? The width of this disk has a central minimum that gives this geometric factor 0.61, and the width will depend on the wavelength of the electrons and the angles and the angle of the aperture, so sine alpha. We're dealing with very small, 10, 20 milliradians, so just a few degrees at most. So sine alpha can be approximated as alpha, and our resolution will depend on wavelength and convergence angle. If we want better resolution, we can either reduce our wavelength or increase our convergence angle to make this value d smaller. So in terms of electron wavelength, we already saw that the wavelength of electrons is very small. Going from 1 volt, we're already at 12 angstroms, to 1 keV. This might be an energy used in an SEM. We're at less than half an angstrom. For transmission electron microscopy, where we need to have electron transparency, we need to get those electrons through the material, we deal with higher energies, and that takes our wavelength down to a few picometers. So 3.7 picometers at 100 keV, less than 2 picometers at 300 keV. And the speeds at this energy is around half the speed of light to nearly 80% the speed of light. So when you're going at, anytime you're comparing your speeds to the speed of light, you're probably dealing with relativistic effects, and that's certainly the case with these electrons. If we look at how the wavelength decreases with energy, we see a non-relativistic equation deviates around the energies we're using in an electron microscope. So when you're calculating wavelengths or dealing with wave equations, be sure to include relativistic terms. Okay, so if our wavelengths are a few picometers, it's probably not the energy of it's probably not the wavelength that's limiting our resolution. Rather, what's limiting our resolution is aberrations in the lens. In the previous lecture, we were introduced to spherical aberration. I'm showing that again here, where at low angles, we have no problem focusing electrons to a sensible point on this Gaussian image plane, but at higher angles for positive spherical aberration, they're overfocused, and we get this caustic curve. And this caustic curve defines a new minimum in the width of our probe that's shifted forward from the optimal Gaussian image plane. And the amount that it shifted, or the amount of this blurring, will depend on our spherical aberration, and it will get worse as we go to higher angles. So if we're dealing, we might have just half a nanometer blurring contribution from the spherical aberration. So we have this competition between opening up our convergence angle to get a better diffraction limit, and then the blurring caused by spherical aberration. In this back of the envelope calculation, we just approximate the shape of our diffraction pattern, the blurring contribution from our diffraction limit, and the contribution from spherical aberrations, each of those as Gaussians, which allows us to add them in quadrature and illustrate how the point spread, how the probe size decreases to a point as we increase our convergence angle, but then eventually is dominated by spherical aberration as we go to higher angles. So we can get an estimate that's functionally correct of what our minimum probe size would be as a function of our spherical aberration and our wavelength. The better approach is to take a wave optical approach. And in this case, we're going to look at the wave fronts of this lens diagram. So we said that the wave fronts are these curves that run perpendicular to the wave vectors, right? So in the aberration-free case, these blue curves represent the wavefront of a perfect lens, where the wavefronts will eventually collapse to a single point that represents the focal plane. However, with spherical aberration, we have this overfocusing effect that causes this plane to bend in more. And we can represent that displacement as this path difference as a phase shift. That is, we typically call chi of alpha. We can pull out a wavelength. We can pull out our wavelength term if we want to represent this as a phase instead of a distance. Or sorry, if we want to represent this as a distance instead of simply a phase. For spherical aberration, this delta S of alpha will increase to the 4th power with spherical aberration. Okay, so, right. What we'll see in the next lecture is that there are many other aberrations. I'm just going to show you a few. We have first order aberration defocus. So this is C1, grows as A squared. We have spherical aberration, grows A to the 4th. And then we have higher order aberrations, C5, and so on. You might hear this spherical aberration also called C3 or CS. Just to be clear that those are used fairly interchangeably. C1 is usually just called defocus. Okay, so what is the game? We want to minimize that phase shift. We want our phase shift to be near zero, ideally zero, over the longest angular range possible. So if we look at how that phase shift propagates out to higher angles, we see that the spherical aberration creates a phase shift that increases quite dramatically. Defocus can be adjusted, so it can go in the negative direction, and we could create a curve that then minimizes the total phase shift, gets it as close to 0. So it's this balancing act where we're trying to balance the phase shift introduced by spherical aberration against the phase shift that can be adjusted with our defocus knob. The wave function across our aperture is now not just this simple 0 or 1 function. It's the dimensions of our aperture as well as the phase across that aperture described by this aberration function. So we would love our aberrations to just be 0, or this phase shift to just be 0. We can't have that. So instead, we try and balance, we try and cancel this spherical aberration with our defocus to keep it as close to 0 as possible over the widest range. We might tolerate a band that's a pi/2 phase shift. This is a quarter wavelength phase shift. And take this out as far as we can until we fall outside of that band. And when we fall outside of that band, our phase shift has gotten too large, and so we just cut it off. And the way we cut it off is we place an aperture. The aperture says anything that has higher angles, don't let it through. Okay, so we can analytically describe how to best balance those two competing forces, defocus and spherical aberration, to get an equation for the optimal defocus as a function of spherical aberration. So the defocus will increase as your spherical aberration increases. The optimal aperture will decrease as your spherical aberration increases. So we need to cut off higher angles if we have large spherical aberrations. And we have our resolution, which is defined in terms of wavelength and convergence angle. So we can create an expression for what our minimum achievable resolution is for a given spherical aberration and wavelength. So at 200 keV, you can get 1.5 angstrom resolution with 10 milliradian aperture and under typical aberration conditions. All right, so what does the information transfer look like in one of these microscopes? We said that we have our aperture function. It now contains some aberrations. So it's 0 everywhere outside of the aperture, and inside it has a constant amplitude, but a phase. In reciprocal space, our contrast transfer function is a convolution of this function with its complex conjugate. If we just ignore the phase terms for a second and we just think about that in terms of a disk, we have one disk and we're convolving it against another disk. So we're pulling these two disks apart, and our overlap region gets smaller and smaller. So we go from perfect overlap down to 0. Okay. So this is a low-pass filter, right? Where we have high intensity at low frequencies, and it goes down to 0 at high frequencies. So right. I should say this is for incoherent. Okay, there. This is for incoherent imaging. This is annular dark. This annular dark field stem would be an example of incoherent imaging. If we change defocus, this contrast transfer function gets worse. So 550 is the optimal. If we deviate from that, it gets worse. We start to damp frequencies at mid-range. And if your defocus is really off, you can actually get a little bit of contrast reversal. You can have values go negative at certain frequencies. Okay. We can do the same type of thing for TEM, and the process is very similar, except where we're trying to maintain a uniform phase shift of plus or minus pi/2 across the lens. We'll get an expression that has the same functional form for the optimal defocus, the same functional form for aperture, and same functional form for the optimal resolution. And again, it's going to decrease with decreasing spherical aberration, and it's going to decrease with smaller wavelengths. But in TEM, the contrast transfer function looks dramatically different. So the information, the contrast transfer function for this A of k is the imaginary term, which now includes this phase term. So it ends up being sine of chi of k. And what a sine function is quite a messy function to interpret in terms of how information is transferred using this CTF. But a sine function, right, it picks up from 0. So it's like a high-pass filter in the beginning. It transmits frequencies over a band, and then eventually will go back to 0, and after which it will oscillate quite rapidly from positive to negative values. So at high frequencies, we have this rapid change from positive to negative. Actual microscopes, a lot of this higher frequency is damped by partial coherence. So you don't have perfect illumination, you have chromatic aberrations. These things will damp off the higher frequencies. But the information that's useful lies in this band pass region. So comparing the coherent TEM imaging with incoherent annular dark field STEM, we see in STEM we have a contrast transfer function that's fairly interpretable. It's just a low-pass filter that goes out to high frequencies. And in the case of TEM, we have 0 transfer at low frequencies. It rises to a mid-band, and then it crosses at a point much lower frequencies than in STEM. However, we get 3 times the amount of information transfer at these mid-frequencies in TEM. So 3 times the contrast over a wide range in the middle frequencies with TEM, but we don't get information transfer out to the higher frequencies. And what you often will do is just cut off information at this contrast reversal. So you might place in STEM, you might place your aperture and say, okay, put the aperture here. I don't want any higher frequencies. TEM, you might put the aperture here. Say, I don't want any higher frequencies because of contrast reversal. In real space, our contrast transfer function for STEM is this Airy disk, and it's the amplitude squared of this TEM point spread function. So the TEM point spread function is the STEM point spread function is 40% narrower than the TEM, so we have better resolution. We also have no values that dip below 0. So if we look at random white noise, we could approximate an amorphous material as just approximated as a random distribution of atoms or intensities in our object function. When we undergo the contrast transfer function of a TEM, which is like this bandpass filter, we get sort of modulation. It looks like sort of ringing patterns that go from bright to dark about this overall gray intensity. Whereas in the ADF contrast transfer function, we see a coarsening of the white noise. So it's like a clustering of intensity, of bright intensities. So it's a smoothing filter. So just to summarize, the contrast transfer function for coherent imaging, you'll have lower resolution but higher contrast. It's easy to get contrast reversals. If you adjust defocus, you'll be adjusting that contrast transfer function will change. The aperture size isn't as important because partial coherence will damp a lot of the higher frequencies. In incoherent imaging, you'll get higher resolution, but you'll get lower contrast at those higher frequencies. It's pretty hard to get contrast reversals, so the images are fairly interpretable. And aperture size is critical. So that's the next thing I want to talk about, is how we choose the aperture for high resolution incoherent imaging. If we look at how our point spread function looks across defocus, so how it changes with defocus, we see at an optimal defocus, we have a large intensity probe. This will give us good spatial resolution, and the intensity decreases and the probe widens. In reciprocal space, we see we have a maximum intensity range over this optimal defocus, over the largest range of frequencies. If we pick the wrong aperture, so 9.6 is a fairly optimal aperture in an uncorrected microscope. If we pick a larger aperture, say 13 milliradians, the point spread function gets a little weirder. We can have two regions where we get a high intensity probe, a central high intensity probe. And so we might be choosing the wrong defocus value to do imaging. So just because you see lattice, if you have the wrong aperture, you may be at the wrong focal plane. If you pick the right aperture, you'll always know. If we look at how information is transferred with the 10 milliradian aperture in an uncorrected system, we see fairly good contrast transfer across out to large frequencies. If we use a larger aperture, we add back those spherical aberrations, and it kills our contrast transfer. So we're getting 50% decrease in contrast, in this case for silicon 111 fringes, if we choose a larger aperture. So just because you see the diffraction limit set depends on aperture does not mean you can indefinitely keep increasing that aperture. Our probe will get worse. At 13 milliradian or at 10 milliradians, 80% of the probe intensity lies within a quarter nanometer. Whereas if you go to a larger aperture, you're out to 0.8 nanometers to capture the intensity of that, the total beam and current closed. So where that intensity goes, it falls out of the central probe that you want, and it goes out into the probe tails. So we just saw this diagram seeing how resolution has increased over time. I want to just note that we're now in this new era of aberration-corrected electron microscopes that correct for that spherical aberration that we've been talking about and allow us to open up our aperture to much larger angles, giving us much better resolution. So now we revisit that phase shift due to aberrations. We're no longer worried about defocus in C3. Because we can now control C3, we're worried about C5. Same game. We want to keep the phase shift as close to zero over the largest range of angles as possible, but now we have additional knobs to turn. We can adjust both the defocus as well as the C3. So we'll pick a defocus value and a C3 value that creates the net phase shift to be within this pi/2 band. And where it exceeds that acceptable phase shift range, we cut it off with an aperture. So now we can already see that before, when we were dealing with convergence angles around 10 milliradians, we're now dealing with convergence angles around 25, 30 milliradians. So what limits us from going larger? Well, our ability to correct higher and higher order aberrations could be one, but we have then we'll run into concerns with chromatic aberrations, which we're not talking about here, but inelastic interactions and beam spread can affect resolution. Inelastic interactions in the case of TEM and STEM, we don't have to worry about that because the lens is before the specimen. However, in both cases, chromatic aberrations due to the beam spread can affect you at higher angles. But before we even get to the effect of chromatic aberrations, we have to worry about the accuracy at which we're able to correct the aberrations at the lower order aberrations. So on the left-hand side, we're seeing an airy disk of an aberration-free probe. And on the right-hand side, we're seeing what happens to this probe if we just add a dash of aberration. In this case, it was a non-symmetric C3-4, and it kills the net intensity of our probe. Our contrast decreases, and that intensity goes out to these asymmetric probe tails. So this is an illustration of, at larger apertures, we're very sensitive to small amounts of aberration. If we consider this aberration corrector to be performing at half the tolerance values it attempts to achieve, aberrations will still kill the performance at large apertures. So in this case, we're doing better than half the tolerance spec of the measured aberrations and the extent which the aberration corrector thinks it's corrected the instrument. And we see that the aberration-free probe, which is the dashed line, does not match the aberration-corrected probe. It's much larger. So with the same game, our integrated intensity gets pulled out to higher dimensions. If we look at our probe size as a function of aperture, this, again, working at half the tolerance spec, our probe size will decrease as we increase our aperture. But then there's a point where the machine becomes very sensitive to small inaccuracies in the aberration correction, and our probe size will increase. So to be conservative, you're probably working in this 22 to 27, 28 milliradian range. This work is, recommend reading the work by Dr. Earl Kirkland if you're interested in seeing how high of an aperture you can get in an aberration-corrected system. Okay, so now I want to jump to the interpretability of STEM images, ADF STEM. So we said that in ADF STEM, we have an incoherent imaging mode. That is, we can think about it as a convolution of our probe, our point spread function, with our specimen. That would be represented by the scanning of a beam across a material. And in the ADF configuration, we're collecting the highly scattered electrons out at high angles. This is a Rutherford scattering regime. So the differential cross-section at high angles is z squared. In reality, what you actually measure is probably somewhere around z to the 1.4 or z to the 1.7. Nonetheless, we have a z contrast image. That is, the intensity of our ADF STEM image scales with the atomic number and the density of atoms when viewed in projection. So if we look at this Wurtzite nanocrystal, we see the heavier cadmium atoms appear as the brighter columns. And we see the zigzag structure corresponding to the Wurtzite. We can see stacking faults. We can see atomic structure down out to interfaces. The Fourier transform tells us the highest frequencies we get in this image, which relates to the resolution. In this case, we see information out to 1.1 angstroms. This is an aberration-corrected tool. For historical reasons, I think it's great to show heavy dopant atoms in silicon. This is an uncorrected instrument. The resolution's not as good as this corrected image, yet we can still see the bright Z contrast scattering inside the crystal. Okay, so detector geometries. The annular dark field gave us this condition for incoherent imaging. We can collect a wide range of electrons after they scatter through the specimen, and we can divide it categorically into two regimes. The dark field regime, where we're collecting electrons that scatter outside of the convergence angle. So this is beta, a bit larger than alpha. And the bright field regime, where we're collecting electrons that scatter within the convergence angle, within the bright field cone. We can further subdivide these regions into high angle annular dark field, which meets this incoherent imaging condition of having 3 times a collection angle, an inner collection angle that's 3 times the convergence angle. Medium angular dark field, which is something less than that, and low angle annular dark field, which I define to be just outside of the bright field cone. Within the bright field, we can have incoherent bright field, which is complementary to the dark field techniques. We collect the entire bright field cone, and further, bright field imaging, which is a detector along the optic axis. It provides coherent imaging condition like that of TEM. And then there's even new detector geometries. ABF is just one example. In the case of ABF, we have a collection angle that is half the convergence angle out to the complete convergence angle of the objective lens. Okay, to see how the intensity of these images look like, we can simulate an image of a single carbon atom. In the annular dark field, we have a bright atom on a dark background. In the bright field, under these conditions, we have a dark atom on a gray background. But the detector space is quite large. We can adjust inner angle, we can adjust outer angle in a scanning transmission electron microscope. This bright field regime is when your outer angle is less than your convergence angle. The dark field regime is when your inner angle is greater than your convergence angle. Within the dark field regime, as we saw, we have low angle, medium angle, high angle. We see bright atoms on dark backgrounds. In the bright field regime, we have, for the most part, dark atoms on white backgrounds in both ABF, IBF, and bright field. However, this is an aberration-free system. If we add a dash of aberrations and change our defocus, optimize our defocus, this coherent imaging regime, this bright field regime, the contrast reverses. Okay, so we like to work with annular dark field STEM because it meets this incoherent imaging condition, because it gives us Z contrast. We get very interpretable intensities that increase with atomic number. So we have a monotonic increasing function in the case of ADF, but in the case of bright field STEM, the coherent imaging mode, the intensity fluctuates rapidly. So we can try to infer chemical information based on the Z contrast with STEM, but it's certainly hopeless in the case of bright field. ABF turns out to also be a fairly interpretable image. If you're interested in ABF, I would suggest reading more about it. It's still being worked out, the conditions which it's interpretable, but it's a promising new imaging mode. So bright field is not directly interpretable. Annular dark field is directly interpretable, and annular bright field may also provide a directly interpretable image. So we said that the intensity depends on Z number in an incoherent imaging system. However, there still is coherence effects that can creep into annular dark field STEM, in particular when atoms get really close to each other. So if we look at the total intensity of two well-separated atoms, we normalize that intensity to be a value 2. As we bring the atoms closer and closer, eventually, once we're past the resolvable limit, so the atoms are now unresolved, there becomes a point at which the intensity increases. And when the atoms are on top of each other, the total intensity increases to 4. Right? This is because at these distances, coherence terms start to come in due to the fact that we've punched a hole in our annular dark field detector. So annular dark field detector does not give you perfect incoherent imaging when you have atoms that are very close. What do I mean by very close? I mean much closer than the resolution of your tool. And this is illustrated experimentally in this strained bilayer graphene system where the bright atoms you see here correspond to 2 atoms on top of each other in Bernal stack graphene. So in Bernal stack graphene, every other lattice site has 2 atoms atop each other. And then we're now pulling those atoms apart. So we're running this in reverse. And what happens is the total intensity decreases. And then it returns back to a maximum when it goes back to atoms being atomically registered atop each other. So this artifact in this particular example ended up being a benefit. It was a way of characterizing the width of these boundaries. In the case of this system, we had both shear boundaries and shear boundaries where the strain is occurring parallel to the boundary direction, and we also had tensile boundaries perpendicular. And using this artifact provided by coherent image coherence, we were able to characterize distances of the 2 different strain types. How are we doing on time? We okay? Okay. So I want to quickly mention the depth of field. So what happens when you start adjusting defocus? We saw that if our aperture is wrong, then things get wacky. But if we select the right aperture, our defocus should just decrease the resolution and contrast as we move away from focus. But what is a tolerable amount? So we can define the depth of field as once the blurring has gotten worse than some resolution D that you're trying to obtain. And that broadening we can think of between 2 spaces can be described geometrically as a 1 over tan alpha, where alpha is the convergence angle of your lens. If we define this tolerable resolution to be our diffraction limit, we get an expression that's 0.61 lambda over alpha squared. This would be for, say, for ADF STEM. And if we go beyond this range, D naught, then we'll start to see blurring effects. So for, just to give some numbers, if we have, say, an absurdly large convergence angle of 50 milliradians, things that are more than 1 nanometer out of the focal plane are going to be out of focus. But for more reasonable numbers, for an uncorrected system, we're talking about 20 nanometers. If you make your convergence angle really small, then you can have a depth of field of 2,000 nanometers. So your convergence angle is affecting your depth of field, and we can see that in the point spread function. So we're looking at the point spread function as a function of defocus for an uncorrected instrument where we have a 10 milliradian convergence angle, and we see that most of the probe intensity lies within a focal range of 20 nanometers. If we go to larger apertures, this is a little too large for an aberration-corrected instrument, but nonetheless, we have a depth of field that's confined to just around 5 nanometers. So when objects are larger than your depth of field, you're going to start to see out-of-focus information. If we look at particles coming in and out of focus. This is a 33 milliradian convergence angle on an aberration-corrected system, and we see particles in one plane that are in focus, while particles on another plane are out of focus. We change our focus, and this is flipped. Now the region that was in focus is out of focus. The region that was out of focus is now in focus. So not all objects will be in focus at the same time, and this is more problematic for aberration-corrected microscopes where you have large convergence angles. You might think that you could do depth sectioning, but there's a caveat with that if you're trying to discern information in two different focal planes that are lying atop of each other, you're going to run into a problem where objects, say this bright sphere on top of this hollow sphere, when reconstructed using through-focal imaging, will give you an intensity that appears inside. This bright particle will appear inside this larger particle. So you can't do through-focal reconstruction to discern, to get true three-dimensional information. And that's reflected in the three-dimensional contrast transfer function of a through-focal image. So we see in the KZ direction, in the out-of-plane direction, we have no information at low frequencies. We have what we're going to learn when we talk about tomography. We have a large missing wedge of information. We're going to see how this plays out when we get to three-dimensional imaging, but it's worth mentioning here that through-focal imaging, at best, can just get you in-focus information in a projection.